What we're going to do this week is have a look at AC analysis using Thevenin's. We're going to do Thevenin's, and I would only ever put in the exam Thevenin's, not Norton's. Okay, we're going to have a look at a question after this. We're going to have a go at a question where there's two sources, and that also requires you to maybe use superposition as well. Okay, that gets a bit lengthy. If I put something in the exam, it'll be something like this. Alright, so we're going to use Thevenin's theorem to determine the current IL in that circuit. So we got some resistance, an inductor, a capacitor that the load is connected across, and I've already put in the two terminals A and B, like we would do if we were doing the Thevenin's process. Yeah. So if you want to get that down. Right guys, so what's the first thing we do when we apply Thevenin's theorem? I'm going to do it to that version. Yeah, we remove the load resistor. So part one of the method. So the first thing we do with Thevenin's is remove the load resistor, the component of interest, leaving two open terminals A and B. Yep. Yeah, well possibly. I mean the question might say sketch what the Thevenin's equivalent circuit would look like for a start, which is going to be one impedance and a source with open terminals and the load resistor replaced. I recommend that you sketch a separate circuit at each stage so you know exactly what you're looking at, rather than just crossing over them. Just sketch it out again. That doesn't have to be really neat. It can be, you know, tag draw quickly, like I've done there in about 20 minutes. What do we know about Thevenin's voltage? What is it? Yeah, it is the open circuit at the terminals A in this case it's the voltage across capacitor. Because if we look at that, when that's open circuit, the terminals here are going to see the voltage that's across the capacitor. So if we can find the voltage across the capacitor, we've got our Thevenin's voltage. Okay. However, unlike the DC problems, in this circuit it's going to be a complex voltage with an angle associated with it. Yeah. And we're working degrees today, by the way, so all calculators in degrees. Not complicated this question by giving you a frequency. I've given you directly XL and XC. Yeah. Okay. So, how do we go about finding this voltage across here, which is V Thevenin's? What do we need to do? So we know that there's only one current in that circuit at the moment because we've taken the load out. When the load is in, there's a parallel circuit. But with the load out, there's no parallel circuit. So we've got a series circuit around here with one current. What do we need to find out first before we can determine the current? Can you modify that slightly, Ben? Is it resistance total? Impedance. Yeah? Just because we got the two reactive components in there, it must be impedance. So first find not Z little t, because that's the Thevenin's impedance. We ain't finding that yet. So what's the formula for ZT in this circuit? It's all in series. Yeah. R1 plus, how did we do it so we can bind the two reactive components together in one go? XL, not quite times, minus XC, close the brackets, J. That's the total impedance of that RLC series circuit. We went for that last week. I think really you'd be expected to know that. Yeah. Because all it is impedances in series. And you should remember that XL is a plus J term and XC is a minus J term. Okay. So put the numbers in that. We got 6 plus 8 minus 3 close the brackets times J, and that's out, which is 6 plus 5 J. Yeah. Now, because we want to find the current using Ohm's law, what do we need to do with that impedance to make it easier? Because we're going to do division using complex numbers. So if we convert that to polar form, what do we get? Use your calculators to do that now. 7.81 angle 39.8 degrees. Yeah. So that's the total impedance of the circuit. So then we can apply Ohm's law using the total impedance. We've got a voltage of 100 volts, angle 0 degrees, divided by 7.81, angle 39.8 degrees, equals 12.8 amps, angle minus 39.8 degrees. How can I do a check on that as to whether it look right? Civil, yeah. What type of circuit is it? Inductive, and we know that because the overall J term is positive. So we're expecting an inductive circuit, CIV-IL, inductive circuit, current lags voltage. Yeah, it comes after we've got a negative angle with the current. Yeah. So that is, the civil check is as expected in this case. Alright. So now we can find V Thevenin's. It's equal to the open circuit voltage, which is the voltage across the capacitor in this case. Yeah. and that is I times XC. We've got to isolate that one component and find the volt drop across it. So we're looking at 12.8 angle minus 39.8. I'm going to multiply that by XC, which is 3 angle, the capacitor in polar form, minus 90 degrees. Again, that's a knowledge thing. You need to know that. Alright? So you do that multiplication. What do we get? We get 38.4. Onions, tomatoes, volts, angle, minus 129.8 degrees. Okay, so that is the first item in our Thevenin's equivalent circuit. So if I just pop forward a couple of slides, we've now determined V Thevenin's as being equal to 38.4 volts angle minus 129.8 degrees. This is Z Thevenin's. So we're going to represent it by a resistor symbol, but it's an impedance and it's going to be complex. So that's the next thing that we've got to find. So, what do we have to do? We've already opened that terminals A and B. How do we determine the Thevenin's impedance? What's the process? Being AC doesn't make that any more complex. What is the Thevenin's impedance? Yeah, we remove the voltage source. And why is it a closed circuit, Nathan? It's the impedance of an ideal voltage source. Yeah. So if that was a current source, what would we replace it with, or what would we leave it as? Open circuit, because an ideal current source has got infinite resistance or impedance, I should be using in this case. So we've taken out source, and replace with impedance of ideal V source, e.g. short circuit. And then what is the Thevenin's impedance then? Sorry? But in terms of Thevenin's theorem, what are we going to calculate to be? What do we need to calculate to be the Thevenin's impedance? Anyone remember? It's the impedance. Looking back in at the terminals A and B with that short circuit and any other short circuits or open circuits in place. So it's the impedance looking back in at AB. So it's what you would do if you put an ohmmeter on these two terminals, or an impedance meter I should say in this case, on those terminals and measured the impedance looking back in. So what kind of circuit have we got there? How's that circuit in terms of series parallel? We're trying to pass the current back in this way. Should take that current off there as well. What circuit have we got? You have got a parallel circuit. Yeah, you've got the capacitor in parallel with the inductor and resistor in series. Yeah. So we need to find, we want to find Z Thevenins. We probably want to use product over sum. Yeah. So we've got R plus XL, those two are in series. I'm going to multiply them, that by XC. Yeah. And then we've got to divide it by R plus XL. That's going to be minus XC J, which we already got that, haven't we, in the first part. So we already know what X. We'd probably be better off if all of this was in polar form. So we know what XC is in polar form. It is 3 ohms angle minus 90 degrees. Just put these in 6 plus 8J, and that is 0 minus 3J. This was 8 plus 8 ohms, 6 ohms, isn't it? 6 plus 8 minus 3J. So that is it. That's the whole thing in rectangular form. We now want to convert 6 plus 8J into polar form. (10 angle 53.1 degrees). And the bottom line we already have from the first part, 7.81 angle 39.8. So to multiply out that top line, that must be 10 times 3 is 30, angle 53.1 minus 90. minus 36.9 divided by 7.81 angle 39.8 degrees. Can we do that division? What do we get? We get 3.84. What are the units, Dom? Ohms, yeah. Angle. Yeah. And that is our Z Thevenin's. Yeah. All follow that okay? Where? No. The impedances from the first part, Z, the total impedance in series from the first part, 7.81 ohms, angle positive 39.8. Yeah. That's the current that's got the negative angle. Okay? Yeah. So we can add that to our Thevenin's equivalent circuit. That is equal to 3.84 ohms, angle minus 76.7 degrees. So now we've got that, we can place our load back in. What value did I give RL in the first place? 25 ohms. We can calculate IL. How are we going to do that? Yeah, we want to calculate ZT. It is RL plus the Thevenin's. If we want to add complex numbers, what's the best form? So we got a Z Thevenin's of 3.84 angle minus 76.7 degrees. Convert that to rectangular. Naught point 883 for J. Yeah, ohms. So ZT is that 0.883 minus 3.74 J. Yeah, Z Thevenin's. That's the total of that series circuit. Yeah. And the rectangular value of the load resistor is 25 plus 0J, and we're going to add those together. So how do we add rectangular numbers? Yeah, you add the real parts together. So we've got 25.883 minus 3.74 J ohms. Yep. We're going to calculate the current, so it'll be convenient for us to put that in polar form. The whole lot, 25. Yeah. There's two questions. Yeah. A long question. Two questions on, no, two questions on the whole, everything we've done.
So, like, something like that.
Yeah, but it could, well, it could be. There'll be something on Thevenin's or Norton's theorem or superposition. And there'll be something on AC analysis like we did last week. Not AC Norton's, no. Could be DC Norton's, but not AC. Right? Only what I've covered in class will I expect you to do in exam. Alright? That shouldn't be a problem. You would normally expect to be able to apply it, but if I haven't done the example in class, I won't put it. Alright, so converting that to polar. Okay, yeah, 26.2. Ohms, angle, minus 8.22 I've got here. Yeah, alright. I mean, ballpark figure for significant figures in the exam is 3. If you go to 3, you won't have any problems. Alright. So we've got the polar, and we can now find IL because it is equal to V Thevenin's divided by the capital V T version of Z total. Alright? So that is 38.4 or minus 129. Sorry? No, it's the voltage. 38.4. What I got here? No.
Yeah.
38.4 volts. Yeah. Right. Z Thevenin's is 3.84. Alright. 38.4 and 29 degrees, that's just by chance. And we just calculated the total impedance 26.2 angle minus 8.22 degrees. Do that polar division and we get 1.47. Angle minus 121.6 degrees. And that's not volts, that's amps. It's amperage. Okay? Now, not sounding convinced. The only issue over Thevenin's, Norton's, etc. with Thevenin's and Norton's with AC circuits is you're fixed at the frequency. If you were to change the frequency, then the value of the reactive components is going to change, and therefore you'd have to redo the Thevenin's process. So at a particular frequency, it's valid. It's valid for any load. Well, I haven't complicated this with frequency. I've given you the values. You could work it out if you knew the values of the inductor and the capacitor, but I've just kept it easier than, and that's what I would do in an exam question. Yeah. Not here to trip you up, just here to test that you've been listening. Yeah. I'm working on it. Okay. In terms of do those angles look right? Okay, we've got a voltage. If that's the starting point and there's 0 degrees, we've got a voltage that's at minus 129 degrees. So there's 90. degrees, and we've got a current that's minus 121 degrees. If we consider that angles go around, is the current leading or lagging the voltage? It's a phasor diagram. No, you haven't got to. I'm just trying to get you to understand that this current in this circuit, right, is leading the voltage. Current's the green one. I. What does that say about the circuit overall? Yeah. Current's leading the voltage, so overall it's capacitive. Okay, I wouldn't ask you that in the exam. I just thought you look at that and you've got two different angles, but you can still find whether the current leads or lags by sketching a phasor diagram with the angles on it. Doesn't have to be accurate, because which one is more negative or more positive than the other, and understanding that the angles are counted as anti-clockwise, and that one's showing that the current is leading the voltage. Okay. With that question on there, what other theorem have you really got to use to be able to do that question? Superposition, yeah. It's two sources. Alright? So, I'll give you a little bit of a step-by-step what you need to do, and now I'm going to let you have a go at it. 1. Remove the load resistor. That's what we do for Thevenin's. 2. Find the open circuit. That'll require superposition. 3. short sources and find Z Thevenins for use equivalent circuit. To find IL. They're the 4 overall steps to doing that. Now the same steps as we went through in the previous question. Any further complication is that you've got 2 voltage sources. That's where you split the circuit into an A version and a B version. Find the 2 currents and add them together. Best way, or what I'm going to do, split my board in 2. Circuit A, circuit B. We're doing superposition here. Terminals A and B. We're going to keep the 6-volt source with the 2 plus 3J there. Take out the second source and replace it with a short circuit. And this is 2 plus 1J. We do the calculations and find VOC for that circuit. VOC for circuit A. And then we're going to keep the 2 plus 3J in there. Replace source A with a short circuit. And that is 4 plus 3J volts. And we're looking for VOC B, VOC A. Superposition, this says, if we find both of them and add them together, we'll have the overall open circuit voltage. Yep. Still just a process. The numbers are more complicated, but the process of doing it is no different to what we've done before. They're both series circuits with only 1 current in as they stand. So, see if you can find the overall V open circuit. Right, I'll just sum up. So most of you got this far now. What we've done here is found the total impedance of a series circuit by adding them together in rectangular form. Convert them to polar so we can use them in Ohm's law to find the current flowing in circuit A, and then use that current with the impedance of just this impedance. I call that Z2A down the bottom. on its own in polar form, so I converted it, and I get that as my circuit for V7's A, and I want it in rectangular form, so eventually I can add them together. Yep. The same process for the other circuit on the other side. So I'll do that one in a little while. So in terms of circuit B, we've got this voltage source driving a current round through the same impedance. There's still the same two components in series. So immediately the total impedance in circuit B we've got already from circuit A. Use that to calculate the current. We've got a complex voltage this time, so I've converted that to polar. Use that polar voltage to calculate the current in circuit B. Use that current in Ohm's law to calculate voltage for circuit B, V7's B. Yeah. I just change everything slightly. I wouldn't. That's close enough for me. Okay. What I've then done, we converted both of those voltages, so V7's A and V7's B, to rectangular form, and then I'm added them together to get the overall open circuit voltage, because that's what superposition says. Add the two components together to get the overall, and converted that back to polar. So I've got a Thevenin's voltage, 4.67 volts, angle 20 degrees. Yeah. So I could add that to an overall Thevenin's voltage, Thevenin's equivalent circuit, where I've found the Thevenin's to be 4.67 volts, angle 20 degrees. And you might be a little bit either side of that, depending on how you're rounded and such like. I don't think it makes any difference. And there's our load resistor added in. So now what we've got to do is find Z Thevenin's. Yeah. So what that involves us doing is going back to the original circuit, keeping the two impedances in, 2 plus 3J, two plus 1J, short circuiting both of the sources, like so, and we want this impedance looking back in there. So it's a parallel circuit of two complex impedances. We're getting short of time. I'm just going to go through this, undo it. So the total Thevenin's resistance is Z1 times Z2 over Z1 plus Z2, which is 2 plus 3J times 2 plus 1J divided by 2 added together, which is 4 plus 4J. Alright, now we can do that work much easier if we have them all in polar form. So converting the 2 plus 3J, which you had already done at some point I believe anyway, 3.61 angle 56.3 degrees multiplied by 2.24 angle 26.6 degrees, and all that is divided by the 5.66 angle 45 degrees that was the total series impedance. Yeah. Multiplying out the top line, I got 8.09 angle 82.9 degrees. Need to divide that by the 5.66 angle 45 degrees. And I ended up with a total impedance, the Thevenin's impedance of 1.43 ohms, angle 37.9 degrees. So that's how you find Thevenin's impedance. And we would then add that into this circuit. So 1.43 ohms, angle 37.9. If you don't get these down, these board notes will go on the website anyway. Okay. So now we've got a simple series circuit whereby we can calculate the total impedance, Z Thevenin's plus RL, 1.43 angle 37.9 degrees plus 3 angle 0 degrees, because that was 3 ohms. Rectangular form is the best way to do that, so I'll convert them 1.13 plus 0.88J. Add a 2, 3 plus 0J. Gives 4.13 plus 0.88J. Convert that to 4.22 ohms, angle 12 degrees. And then IL is equal to V Thevenin's over the total impedance, 4.67 angle 20 degrees divided by 4.22 angle 12 gives me a current of 1.11 amps, angle 8 degrees. Right. So, yes, it becomes a bit more long-winded mathematically and uses up a lot of paper, but Thevenin's with an AC circuit and superposition still uses the same process. Still requires this understanding of replacing sources with their ideal impedance. Okay? So